All right, now finally we're going to move on to the interaction picture, and this is what we're going to find the most useful for quantum field theory. In the interaction picture, we allow for some change of both the operators and the states. Suppose H equals H naught plus HI, where we have a Hamiltonian that's broken into the main part, which is H sub 0, the free part, and then a smaller perturbation to it called H sub I. And let's suppose also that we have quote unquote solved for H sub 0, meaning we found the eigenstates and eigenvalues of the Hamiltonian when the Hamiltonian was only H naught. In the interaction picture, here's what we assume. We assume that the operators still change, but they change in this fashion. This is very similar, if you look at this, to the Heisenberg picture, where you have the operator at any given time t, and here let's just assume t sub naught, or t naught, t sub 0 is 0, so we can get rid of that little extra factor. And then the operator in the interaction picture, and I have an I for the subscript for the interaction picture at any given time t, after the reference time, is equal to the Schrödinger operator, and it's multiplied on the left by e to the plus I h naught t, and multiplied on the right by e to the minus I h naught t. Now this is just like the Heisenberg picture, except with one difference. We're using not the whole Hamiltonian, but just the h naught part, both on the left and on the right. So it's similar to the Heisenberg picture, but instead of the full Hamiltonian, which is h naught plus hi, we just use h naught. The states also change in the interaction picture, and the way the state changes at the state at any given time t is related to the true state, which, quote unquote true in quotes, because you can't really say one's true or not if they give identical physical prescriptions, but I like to think of the Schrödinger picture as quote unquote the true picture, just for reference. So the state at a given time t in the interaction picture is equal to the true state, or the Schrödinger state, at that same time, but now pre-multiplied on the left by e to the plus I h naught t. Again, similar to the Heisenberg picture, except remember, note the h naught here. Now, a few things to note. First, note that this thing, h sub I, the interaction part of the Hamiltonian, is not going to be equal to h sub I in the Schrödinger picture. So h sub I in the interaction picture, which here I just wrote h sub I comma I, or int, just to be clear here, is not going to be equal to h sub I in the Schrödinger picture. In fact, this is the actual definition. H sub I in the interaction picture is equal to h sub I in the Schrödinger picture, pre-multiplied, of course, just from this formula for any operator, but pre-multiplied by e to the plus I h naught t, and post-multiplied on the right by e to the minus I h naught t. Pay attention to the notation because it gets a little tricky, but we're going to eventually be using the interaction picture all day long, so we're going to get tired of writing hi comma int. So when we write just h sub I, which really means this part over here, this perturbation to the Hamiltonian, we mean this perturbation, but expressed in the interaction picture. So just later on, it'll be nicer, instead of having to write things over and over again, but technically we should write h sub I kind of thing. But the h sub I is the perturbation of the Hamiltonian, but when we just write it like that without a HP or INT at the end of it, without that, just means HI in the interaction picture, which technically is different than the HI in the Schrödinger picture, which is kind of the picture we've been starting along. And by implicit assumption, this was the original HI we've been talking about before. It's just a good summary of showing you now the three different pictures. We talked about the Schrödinger and the Heisenberg picture. Remember, in the Schrödinger picture, the state changes, but the operators never change. In the Heisenberg picture, the exact opposite. The state never changes, but the operators change. And in the interaction picture, we have a little bit of combination of both. Both the state changes and the operators change. Here's kind of a crude picture of the interaction picture. So if you think of, we have a vector or a ket in our Hilbert space. I just drew it in this weird two-dimensional picture. Don't imagine much about the dimensions, because a Hilbert space is infinitely dimensional, but just for diagram pictures, let's just say our current state of our system, our ket in our Hilbert space, is represented by this green arrow at time t0. In the Schrödinger picture, the state will evolve to some new state as time goes on, so at some later time t, instead of t naught, this vector If it's not an eigenstate of the Hamiltonian, will kind of evolve to something different, like this over here. And that's getting evolved by the full Hamiltonian, h equals h naught plus hi. But in the interaction picture, what ends up happening is you have also evolution of your state and your operators, but the state itself, and showing this crude picture, just the state itself won't evolve as much. So let's say the state, in the Schrödinger picture evolved all the way out to here. It opened up by this angle. In the interaction picture, it won't quite go that far. It maybe only goes this far, as opposed to, this is just this dotted line is where the Schrödinger picture state would have been. And the reason is that because you're basically, once you have this state, when you look at our definition for the state, you pull it back by plus IH naught t. So that factor of plus IH naught t kind of pulls back this vector, so to speak, to an earlier time, but it pulls it back by the amount, not the full Hamiltonian, but plus IH naught t. So it pulls it back to here. And then the only thing that actually made this move forward is actually HI. So if you look at these things, and we'll get into a little bit more of it in a moment here, HI is actually the way we set things up in the interaction picture. HI, again, is HI in the interaction picture. So it's HI comma I or HI comma INT. That's what causes this to evolve forward, not the full Hamiltonian. It almost gets pulled back by H naught. So that's the basic idea of the interaction picture. That we adjust things so that it's only HI, the perturbation small part of the Hamiltonian, that's actually evolving our vector. There is a type of Schrödinger equation for the interaction picture, and I'm just going to restate things here. So this is the interaction picture definition over here, this first line for our kets. You pull back your Schrödinger ket by e to the plus IH naught t. And if you just invert this or multiply this by e to the minus IH naught t, you get the formula kind of in reverse, where you get the Schrödinger picture in terms of the interaction picture ket. Now, let's start with what we know is always true, the Schrödinger equation for anything, whether it's QFT or anything else. And this is in the Schrödinger picture. We have the Schrödinger equation. I'm putting these subscripts S's because now we're going through different pictures and we should just be explicit. So this is the standard Schrödinger equation. I d dt of your ket is equal to the full Hamiltonian acting on the ket again. This is the differential equation that we know determines time evolution in quantum mechanics expressed in the Schrödinger picture. Let's try to express things in the interaction picture, and we'll use our formulas and plug stuff in. So first of all, this here, this ket in the Schrödinger picture, we can use this formula for it to expand this out, and now we have this formula here, and we have to switch this ket to the interaction picture ket with this factor of e to the minus IH naught t. And then on this side, same thing. I keep the H naught plus HI comma S, and I'm assuming that my original interaction is given in the standard way in the Schrödinger picture, which would make sense. That's what we were thinking is the true way of doing things, and the perturbations will be defined that way, at least to start with. So I wrote this subscript S, and then this thing over here I just rewrote again using the same formula. We'll keep grinding things out. Now, if I take the derivative of this expression, this is a time-dependent function, and this is a time-dependent ket. So I will actually use the product rule here of the derivative, where I'll take the derivative of the first multiplied by the second plus the first multiplied by the derivative of the second, which you remember from basic calculus. We could apply that here to this expression, analogous fashion. So if I take the derivative of this term, the minus IH naught gets pulled out in front of this exponential, and then the rest of the exponential stays the same. And then I still have the original second term. Plus, now I'll take this derivative applied to the second term. So I'm going to leave the first term the same, I e to the minus IH naught t. That's the first term, and then the derivative of this ket. Remember, now this is time dependence in the interaction picture. They're both time dependent, the operators and the kets. And on the right side, I'll just kind of rewrite what I have here, but just expand out this addition sign to H naught e to the minus IH naught t, and this interaction ket right over here, plus I expand this part out over here. So right over here. Now, if you take a look at this, I times minus I gives you 1. That's something you should just generally remember. I times minus I gives you 1. Then if that gives you 1, then I just have this expression H naught e to the minus IH naught t acting on psi sub I, and then the same thing over here, and then those two things will cancel. And here's, now if I multiply both of the, now I have this equals this, and if I want, I could multiply both of these expressions by e to the plus I h naught t on the left, and I did that here. This I could just get pulled out, and that those two expressions will cancel or end up being e to the 0, which is identity. So on the left, if I do that pre-multiplying, I get this expression here. And on the right, if I pre-multiply it, I just wrote it out. I get e to the plus I h naught t, this thing, e to the minus I h naught t, and the ket in the interaction picture. Now, if you look at this, this is our standard definition. Here's an operator, in this case, expressed in the Schrödinger equation. In this case, it's hi, the perturbation to the Hamiltonian in the Schrödinger picture. And I pre-multiply it on the left by e to the plus I h naught t, and post-multiply it on the right by e to the minus I h naught t. And that is just the definition of this. This whole thing is a new operator that by definition is the interaction picture operator. So this is h sub I, which I can write h sub I comma interaction, but as I mentioned, I'm just going to write h sub I because that's going to be our workhorse in the future here, in the near future. So this whole thing then is this. So this is a new formula, which is really looks just like the Schrödinger equation, but now it's in the interaction picture. It says I ddt of this ket of my current state, expressed in the interaction picture, is equal to h sub I, which is the perturbation part of the Hamiltonian, expressed in the interaction picture, acting on the same ket over here. This is my differential equation. Ultimately, what we're going to do is we're going to try to solve this for this ket over here. This is going to give us all the information that we want. That's going to be our goal. I kind of double start this. Let's now finish those general considerations which apply to any quantum mechanical system, where we talked about Schrödinger picture, Heisenberg picture, and interaction picture, and now try to apply some of these ideas directly to our QFT model that we've been working on for many lectures now. So I just will acknowledge that in QFT up until now, we've been implicitly working in the Schrödinger picture, which is quote unquote the standard quantum mechanical framework, as I talked about. All of our operators that we've talked about before, like phi, with x with the hat on top, with a vector arrow on top of it, pi, and di, partial I of phi, all with vector hats on top of it, are unchanging in time. You remember, these are our guys we've talked about for many lectures in the beginning. These are our main operators, and these were not time dependent, and these were all expressed in the Schrödinger picture. These are all, there's an operator at every voxel, operator at every voxel, operator at every voxel. Each of those are operators on the whole Hilbert space, well defined, and they have no change in time. They're also expressed in the Schrödinger picture in everything we've said before. And so far, the way we expressed it before, only the ket representing our state evolved in time, according to the full Schrödinger equation using h equals h naught plus hi comma s, and the perturbation part right now is still expressed in the Schrödinger picture. Now, we're going to change our whole approach and change from the Schrödinger picture to the interaction picture. Ultimately, this will be the picture where we do all of our work in quantum field theory. So remember, this is an operator. This is defined at every voxel. So there are lots of these operators, but for this particular voxel called x with the arrow on it, the name of the operator is called phi of x. We're going to change that from the Schrödinger picture to a time-dependent picture, which specifically will be the interaction picture. So I'm going to change this to, this is the notation, phi of x comma t, which now we just write phi of x. If I have an x with the vector on top of it, it means a three-dimensional vector, a spatial vector. If I have an x with no arrow on top of it, it's a four-dimensional thing, which is just an abbreviation for x, y, z, and t, or typically t expressed first, and then x, y, z. So I kind of have this backwards. Usually this should be t and then an x. And by definition, I just take my Schrödinger picture, which is this original guy here. I could put the subscripts s if you want for clarity, but that was implied the whole time. And then by definition, if I want to convert to the interaction picture, all I do is I take this operator and I hit it on the left with e to the plus I h naught t, and on the right with e to the minus I h naught t. I do the same thing for every other operator, the pi's and these guys. Now, let's re-express the operators phi x in the interaction picture. where, unlike in the Schrödinger picture we've been working thus far, will now show a time dependence. These things never showed a time dependence. This is the formula I was talking about, and let's use it in terms of our famous A and A daggers that we talked a lot about. So I'm going to just keep this e to the plus IH naught here and e to the minus IH naught here, and I have brackets on this thing, but this is just this thing re-expressed like we talked about in previous lectures. This is the expansion in terms of A's and A daggers right over here. Okay, so this is this whole thing expanded like we're used to before. And now I'm just going to kind of crank out a bunch of math here, and we'll try to be as clear as possible. So if I start expanding things out, I just take this thing and I hit it on here and I distribute it out to this side. So there's two terms, e to the plus IHT naught here. Here's this original term here, just so you can track with the yellow lines. And then I post multiply it by e to the minus ITH naught. So that's how I got this whole first term, this times this times this. And I put that sum over here. And then I'll do the same thing over here. It's still the same sum over P, but I pre-multiplied on the left by e to the plus ITH naught, sum over P, this prefactor, then this whole thing over here, and post multiplied over here. So that's pretty clear. Now I can kind of manipulate things. The operator parts, if you look here, this is an operator. It's exponential of an operator, but it's an operator. This A sub P with the vector on it is an operator, and this is an operator. This stuff is just a number. This is numbers. So I can put all the operators next to each other and pull the numbers out front, which is what I did. And now I have this expression. This thing shakes down to this, e to the plus ITH naught A sub P e to the minus ITH naught over here. And the same thing I do over here. I pull all the operator stuff here, and I have a similar expression, e to the plus ITH naught A dagger sub P e to the minus ITH naught. So this, and all these prefactors. Now our big task is to calculate this thing, this expression over here, and this expression over here. This is the non-daggered one, and this is the daggered one. E to the plus ITH naught A sub P, e to the minus ITH naught. I'm going to show you that on the next slide. First, I can actually just realize, if you just look at it by definition, this whole expression, which is the one we're about to calculate, and this whole expression, this just is the definition for A sub P in the interaction picture, right? That's how we did that. We took any operator, we multiplied it, e to the plus ITH naught, e to the minus ITH naught. So technically you can phrase it like this. We're probably not going to use this that often, but just something interesting to note. And similarly with this over here. But we need to calculate this guy over here and this guy over here. Right? And when I just write A sub P and A sub P, that would be in the Schrödinger picture if we hung around with this, but we're going to keep moving forward. Well, we need to remember two things. We showed this before in the previous lectures, that if we take the commutator of H naught with A sub P, and we knew the expression for H naught, remember it was the free Hamiltonian, that was the sum of omega P, A dagger, A P subscripts. But if we took the commutator of that with A sub P, we got this expression over here. We showed that in the previous lectures. And if we take the commutator of the H naught with A dagger P, we get this, plus omega P, A dagger P. Now we're going to use something which I'm not going to prove, but just going to be given. It's called the Hadamard lemma, and that's this over here. This is true for operators in general. You could probably look online for a proof of this. But this is true. I have e to the, if I have operators A, B, and A, if A and B, then this statement is true for this expression over here. Now, if we just start looking at this expression and plugging things in, remember this is, let's first calculate this part over here. This part will just show the result on the second side, but it's the same argument, but we're going to do this part over here. Let's just let A in our expression equal plus ITH naught and B equal A dagger P. And if you look at this expression in terms of these definitions of A and B, you get exactly this over here. And then we can say that this, we can use this formula. So e to the plus ITH naught, A dagger P, A sub P, e to the minus ITH naught, this part over here, that's equal to, I'm just going to plug the formula into B, which is, this part over here, A sub P, plus the commutator of A and B, and A is this, plus ITH naught, comma, A sub P, plus 1 over 2 factorial, and then the commutator of the commutator, so plus ITH naught, which is my A, comma, and then the commutator of A and B, and A again is this plus IT H naught, comma, B again is A sub P, and then plus so on and so forth. And we just show the first few terms. The rest will be clear. Now, here we use this formula over here. Remember, if you have the commutator, and you have operator, and just some number, you can pull the number out front of the commutator, so that plus IT. So then I just have the commutator of H naught with A sub P, and we know that formula here that we've proven and used a lot before. This gives us minus omega P A sub P. Same thing over here. We could pull out the plus IT and get the minus omega P A sub P. And then we have the commutator of this with this, and again, the plus IT and the plus IT and the minus omega P can get pulled out of that whole thing. And this whole expression then is just going to be the commutator of H, that thing pulled out front, which is the plus IT, this pulled out front, this plus IT pulled out front, this minus omega P pulled out front. And now you just have the commutator of H naught with A sub P, which again, we use this formula here, which is again minus omega P A sub P. So you can take a look at that, but that's just following this exact thing here. And now if we just kind of condense terms and rewrite this, A sub P minus IT omega P, A sub P plus 1 over 2 factorial. And this whole thing is the final expression. And I'm just going to write it as plus, as this is a minus. This is going to cause, this is a minus and a minus. So that becomes plus, and you can get rid of this minus if you want, but I'm going to just write it like this as minus IT omega P minus IT omega P, and this is a minus IT omega P, the whole quantity squared, and then A sub P, and then this whole thing will repeat if you follow this formula all the way out. So let's factor out the A sub P, and then I have A sub P 1 plus minus IT omega P plus 1 over 2 factorial plus that same factor minus IT omega P quantity squared, so on and so forth. And this whole thing here is just a number, but it's the exponential. It could be, this is the exponential series right over here, or the exponential sum, and that's gives me my final expression. That this thing that we were trying to calculate, this guy over here from our previous result, is just nothing but can be all condensed down to A sub P e to the minus IT omega P. So that's summarized over here. And exactly the same argument, you could play around with it on your own using that Hadamard lemma. Probably good practice to do that. Do the same thing for A dagger, and it's just an analogous argument, and you'll find this expression here, a very similar expression with the plus IT omega P. So going back to where we were, and now we're going to start to use the standard notation again, where if I have a phi with just an x with no arrow on it, this is a four-dimensional vector, and this is going to, by definition, be in the interaction picture. I won't even write I anymore because that's going to be the picture, that's going to be our workhorse, and we're just going to use it over and over again. Now we get this. This was going back from 2 slides. Remember, we had this expression over here. This was where we were. If you look back in a couple of slides, this was the whole expression, and we were trying to calculate this term and this term, and we did now, and the results are up here. And this whole term now is just symbolized by A sub P e to the minus IT omega P. And this whole thing here is just this guy over here, A dagger P e to the plus IT omega P. And then if we start kind of cranking things out more, we can pull out the AP over here out front, and then just combine these exponentials. We have e to the plus IPX, which I wrote in this way, e to the minus I, and then a minus px. P dot x is 3-dimensional vector dotted with 3-dimensional vector, which is really pi xi. When we write it, our symbols are running around from 1, 2, and 3 by convention. If we use English symbols like I and J, it's 1, 2, 3. If we use like the Greek symbols like mu, then it's 0, 1, 2, and 3. But that's what this means. And there's a summation applied here. That's what this dot product is. This minus and minus becomes this plus. And then this minus over here, minus IT omega P is right here, minus I. The minus I is there. The T omega P is over here. T is x naught. Remember, x naught is our time dimension, so that's what T is. X naught equals T and omega P, so that's where this expression comes from. And the same thing here, we just worry about the sign difference here. Here I have an A dagger P, which goes here, and then e to the plus IT omega P, which is the plus over here, and e to the minus IPX, and this and this will become a minus. Sorry, there's one extra I that doesn't need to be here. over there. So that's that expression over there. Now, just remember things when we're playing around with four vectors, which becomes important, but once in a while to be clear. I mentioned that x naught is equal to t, and then a standard four vector is given with the index upstairs, the contravariant vector in special relativity. That has four components. And when I say p, the momentum one with its thing listed as a superscript, I first mean the energy, so omega sub p, and then the three different components of momentum, x, y, and z, and this is the standard way of doing it. And when I just write the word x, I mean x naught, x1, x2, x3, so time, x, y, and z axis, but these are the ways. So the first component of this four vector is always the time. The first component of this four vector by convention is the energy. And if I want to get a downstairs vector, if I want to change this from contravariant to covariant in the language of relativity, then with the metric that we're using, you never change the first component. It's the same thing, but you have to change all of the spatial components of the second, third, and fourth components. So you put a minus sign in front of them. So this is technically this guy brought downstairs. P sub mu is different than P super mu in terms of these guys become minus P1 minus P2 and P3. It's just an important thing that comes up over and over again when you calculate things in QFT. And then this expression is also very, very common. When I just write px, technically means the whole vector p and the whole vector x, and they're just inputted into the four-dimensional dot product, which is this. One is downstairs, and the other is upstairs, and you're contracting the two. And then if we just expand it out using these definitions, that's equal to p0 x0, and then this, remember, is pi upstairs, but negative that, so that's where this minus sign comes from. And this I over here, and there's a summation 1, 2, and 3 over here. So that's what this term means, p naught x naught minus pi xi. Take a look at that. This is not hard, but it's a pretty common convention that will come up in QFT over and over again. And sometimes instead of p naught, I'll just write omega p, because p naught is the energy, which we're writing as e sub p or omega sub p sometimes, which is what we have here, x naught minus pi xi. So if you put all that together with our new notation, here's our final formula. We now have our operator phi at this voxel x at a time x naught. So now this is now time dependent. This is in the interaction picture. We could put an I here, but we're not going to, because that's going to be the convention. And we have now transformed our phi x operator to a time dependent operator in the interaction picture, and this is the simple way of writing it. It's almost the same expansion that you saw before, except you have an a sub p, and now you have to write it like this, e to the minus ipx. If you just play around with the minus signs, you'll see why the minus sign got changed here. It used to be plus here. That was only when you had the spatial parts. And now a dagger sub p, in the plus is here, plus ipx. And these are four-dimensional expansions, p0, x0, plus pi xi. Same thing over here. This formula is worth memorizing. I'm not a big memorizing kind of guy, but sometimes just easier to remember this. This is in the discrete form. There's also analogous things in like Todd's lectures, which we still will use from time to time in the continuous form. Remember, I told you we're going to go back and forth between discrete and continuous, but this formula is worth memorizing. And notice that there's a time dependence, because there's a time, includes a time component, and this includes a time component. That time component is also implicit here. So this is our big thing. Here's our equation that we have over here. We know that we have a Schrödinger equation for our state in the interaction picture right over here. And now we know that our big operator, phi sub x, we can express this way in the interaction picture. And these two equations will ultimately allow us to calculate how our initial state changes under the action of h sub I. So if you look at this equation, remember we're given our h sub I in the Schrödinger picture. Initial perturbation is given in the Schrödinger picture. And for example, I remember I talked about it before, there's different books where you use different toy models. The one we're going to use is the phi fourth model. So we're given that the perturbation part is lambda over 4 factorial phi sub s raised to the fourth power. And now I just put the sub s because that was implicit in the Schrödinger picture. That's how the perturbation is given. And of course, we integrate this over all space for the full Hamiltonian. And this is our perturbation. Now, one thing I'll just show, it doesn't always mention this in books that clearly, but it's worth knowing, is that we really technically need not h sub, for this formula, which is what going to be our Schrödinger equation that we're going to use, we need h sub I, not h sub I comma s. We don't want the Schrödinger picture, we want the interaction picture of h sub I. But it turns out you don't really have to worry too much if you forgot about this, because you pretty much get a very similar thing. But we can use exactly the same form as h sub I sub s for hi, but substitute 2 in place of phi sub s. So I'll show you what that means. Technically, h sub I in the interaction picture, I take the h sub I in the Schrödinger picture, pre-multiply it on the left and the right by h sub naught. But if you crank all of this out, if you look at this, here's the definition of this, and that's the integral, which I now pulled out in the front, and same with the lambda over 4 factorial. And now I just have e to the plus I h naught t, and the 4 factors of phi over here. These are now in the Schrödinger picture, not time dependent, and e to the minus I h naught t. But if you keep cranking this out, you can do this little trick here where I have this phi, this phi, this phi, this phi, but sandwiched between these two phi's in this expression, I put the number 1, or the identity operator, which I'm another name for is e to the minus I h naught t, e to the plus I h naught t, because there's nothing with the identity. I do the same thing here. I do the same thing over here. And now if I look at this expression, I just continue this derivation on the next slide, which is right over here, I can group things together and realize that this whole thing now here is just the definition of the interaction picture for phi. So phi x without the vector arrow on it. Another thing over here, phi x without the vector arrow, phi x without the vector, phi with x. So these are phi in the interaction picture. So technically, if I started with that Schrödinger picture h sub I perturbation, this is the actual formula for the perturbation in the interaction picture. This is pretty much the same expression. The one difference is that this is now time dependent. It wasn't in that initial perturbation, but the rest of the way the expression looks exactly the same. Like if I made a mistake and didn't realize I really have to use the hi, which is what the Schrödinger equation for the interaction picture was that I showed before, then it kind of gives out the same expression. So one last order of business. We will soon show a powerful technique in the next lectures in quantum field theory to perturbatively solve this Schrödinger equation. This Schrödinger equation, of course, is the one using the interaction picture. When we eventually solve this in the next lecture, the technique will yield the ket at a later time after the interaction is done in the interaction picture. So I call it psi sub I. And it's not going to be the Schrödinger picture. Remember, when we really started talking about interactions and what we measure at the beginning of this lecture and in the other lecture, what we were really talking about is the standard picture, and our interpretation was in terms of the standard picture. In other words, we really wanted to calculate after the interaction is done using h naught plus h sub I. We wanted to really know what the ket was in the Schrödinger picture, not in the interaction picture, because we have a real interpretation of how to interpret our results, as we even talked about at the beginning of this lecture. So we should, in principle, therefore, whatever technique we're going to use here, which I haven't went over yet, once we use that to crank out what psi is in the interaction picture, after all of our interaction is done, we should technically have to convert that back to psi in the Schrödinger picture. This part took me a long time to really look at and analyze and try to understand what was going on, to kind of figure things out a little bit on my own. But books usually don't talk about this. They usually just give you the final answer here, and then just you start interpreting that in terms of the physical results and interpretations we mentioned. But technically, you should have to convert it back to the Schrödinger picture, or so it seems. It turns out you really don't need to do that for this particular reason, which I want to show. What we're really going to do in quantum field theory is we're ultimately going to calculate things that are called transition amplitudes, meaning that you have this interaction, you let it go on for a certain amount of time, and then you see what your final state is and what the probability is of measuring different Fock states. The Fock states are what you measure really in the detector. So let's just say the final state after all the interactions in the correct or true picture or Schrödinger picture is this, psi sub s. This, of course, will be a superposition of eigenstates of h sub naught, because this is still a basis vector. So this is a superposition of Fock states. When we do our measurement, if this is our final state after our interaction is done, and we use our calculational tools to figure out what this actually is at the final time after the interactions are done, we want to know what these different coefficients are. So we want to know what are the chances of measuring 1p1. or the chance of measuring 1p3 and 1p4, or so on and so forth. So all we do is basically we take the inner product of this whole thing with what we're interested in, and that'll yield out the coefficient, the modulus. That'll yield out the coefficient, which is what we really want to calculate. We'll eventually take the modulus of that squared. I'm here just calling that SFI for kind of like a transition amplitude. That's the type of thing that we're ultimately interested in. So these are the Fock states, and this is in the Schrödinger picture. And this we have defined or delineated a very clear physical interpretation. But again, we use this Schrödinger picture over here. The Dyson formula is what it's going to be called, what we're going to use to kind of get our answers here. But as I mentioned before, that's not going to yield this in the Schrödinger picture. It's going to yield this in the interaction picture after the interaction. But let's look at this part now. Remember this relationship. According to the interaction picture definitions, psi in the interaction picture is defined to be equal to e to the plus I h naught t acting on psi in the Schrödinger picture. That's the definition of this. So let's look at this formula here, which is what we want, and plug in this formula over here. Or to solve for psi sub s, we just kind of invert this or multiply this by e to the minus I h naught. And this is what you will get. And then you could plug this in for this, which gives us this for SFI, which is what we want to ultimately calculate. I'm going to put this on the next slide over here. That's the same expression. But look at this now. This is e to the minus I h naught t. This is an operator sandwiched between a bra and a ket. And we know from quantum mechanics, the math of quantum mechanics, we can apply this operator to the right or to the left. You can do that in quantum mechanics. You can apply it to a bra. And if we apply it to the left, this is just nothing but an eigenstate of h naught. That's the whole theory we developed earlier before we started talking about interactions. This is a Fock state. So let's apply it to the left. Once we apply this to the left, we'll get this expression over here. This is an eigenstate, so we'll get the same state back, 1p1, 1p2, but now this h naught will be converted into the energy of this state, which is ep1, p2. So that's e to the minus ep1, p2, which is just a number in that same state or bra. Now, what that means, and so this expression that we're interested in basically is this right over here. You can pull out that factor right over here, which is just a numerical, which is just a number, and then you have this inner product between this and this. Now, when we actually calculate things in quantum mechanics, we're going to take the modulus of this, and the modulus of that squared will give us our transition amplitude, the actual physical probability that we'll experience this result when we're sitting in this state. So what this ends up meaning is that this final transition amplitude, this thing over here has a modulus of 1. It's just a random phase factor, so that drops out. So our final transition amplitude will really be this. So even though we're going to use a big formula to give us the interaction picture ket, and we should be converting that to the Schrödinger picture ket, we actually don't need to do that because we'll end up getting the same result. And this is why it's not really mentioned in many of the quantum mechanics books that I've read, but this is why you don't actually have to do that. Without getting way off tangent, I'm kind of hitting quantum field theory at like a level 1 for our QFT 1 course, where we talked about interactions and its potential big weaknesses. As we get to QFT 2, we'll talk about kind of probably more accurate ways of extracting transition amplitudes and information from Hamiltonians without making some, very dramatic, dodgy assumptions. But anyway, this assumption is made very commonly in QFT 1 courses, and now you know why you don't actually at the end have to convert this to that. We'll show you more later on when we do all this math to figure out what this ket actually is. It really technically is the interaction picture, and our physical phenomenon really were defined in the Schrödinger picture, but it's okay. To summarize the entire talk, which was a pretty dense talk, remember, the general framework for quantum mechanics has statements like the probability of measuring this value, omega sub I, for an operator omega is you take the ket omega, you take the bra omega sub I, and hit it with the ket of the state that you're actually in, and that tells you the probability, especially if you take the modulus. If you take the modulus of the square, that's really what gives you the probability. But those are the statements we always say for quantum mechanics that are true at any time, regardless of what picture you're in, and similar statements that we're all familiar with. When a system evolves in time, which will be true for our QFT interaction model, we don't have to stick with our, quote, standard or Schrödinger picture model. Other models give you the same physical results, but maybe better mathematically. We talked about the Heisenberg picture, which gives identical physical results. In particular, for our situation that we have in QFT, where we can't solve the problem exactly, but we can solve for H naught being the Hamiltonian, but not H naught plus some perturbation H sub I. The interaction picture is the other picture we use, and that works well. Here, H naught is the things we talked about. H I is something small. The classic example we're going to use is this toy model of phi to the fourth model, of which is this is the interaction Hamiltonian density. And now, even within that, remember, we define our perturbation in the Schrödinger picture because that's the one we're really most familiar with. And that technically, this is what you would get. But it turns out you can almost use the same type of form and just show that this is the same thing in the interaction picture, which is what we need when we use our Schrödinger equation expressed in the interaction picture. So, it's HI in the Schrödinger picture, HI in the interaction picture, which we just called HI, is almost the same thing, except this now becomes time dependent. And we talked about the formula for the time dependence of phi, which is a very important formula. This is now in the interaction picture, the new operators phi x. There's still one for every voxel, but now these also change with time. And that's why we symbolize this without the three-dimensional vector arrow on top of it, but just an x, talking about 4 dimensions here. And this is the formula I wanted you to remember. As we talked about, there's a new Schrödinger equation in the interaction picture, which has almost exactly the same form, except everything's in the interaction picture. Here, the ket is in the interaction picture, and the Hamiltonian perturbation, HI, is in the interaction picture, but happens to have the very same form of this, which is actually in the Schrödinger picture. These 3 equations become very important, and they'll allow us to solve perturbatively in the next lectures, ultimately for this ket, at the final time after all of our interactions are done, called t. For the purposes of our calculations we care about, scattering amplitudes, we can still just use this instead of the really technically more correct this, which is the Schrödinger picture, since when we actually calculate the transition amplitudes by taking the inner product of this with Fock states to calculate probabilities of getting different particular results in our particle accelerator, they give the exact same scattering amplitude and probability.